There is a bit of an education process that's needed to understand orbital dynamics. Because a lot of people are confused of like, why the heck are you landing landing a rocket on a ship in the ocean? That seems pretty inconvenient. And the reason is because that going up and staying up is actually about velocity horizontal to the Earth's surface. So there's a huge difference between space and orbit. It's like space you could think of as like, say, being the international waters boundary for the Pacific Ocean. Like if you go, 100 miles offshore, you're technically out of coastal waters. Now you're in the Pacific.
Right.
So it's like technically you're in the Pacific, but orbit is like circumnavigating the globe. Right. It's a really giant difference, and the reason that things go up and stay up is because you're zooming around the Earth so fast that your outward radial acceleration is equal to the inward acceleration of gravity. And so those balance out and you have a net zero gravity. So when you see the space station, the thing that's a little sort of counterintuitive is that the space station is actually zooming around the Earth at 17,000 miles an hour.
Even though it seems like
it seems really still, but it's moving really, really fast. I mean, to put that into perspective, a bullet from a .45 gun, handgun, is just below the speed of sound. So the space station is going more than 25 times faster than that. And that's what's needed actually to go up and stay up. And that's why there's the term escape velocity, not escape altitude. There's no such thing as an escape altitude. There's only an escape velocity.
You need to be a certain speed to escape the gravity of the Earth.
Yeah, you can think of gravity as kind of a funnel in space-time. Or think of like a coin funnel. Like it's very much like that but it's obviously a sort of a four-dimensional coin funnel. But if you spin a marble or a coin on a coin funnel, when it's far out, it sort of spins slowly, and then as it gets closer, it spins faster and faster. And if you were to start at the bottom of the coin funnel and you wanted to exit, you'd spin it horizontally, and it would spin out, and that's really how you get to orbit. So the gravity well is like a funnel.
Why you want to land on a ship in the ocean?
Because in order to get to orbit, all that matters is your horizontal velocity. Your altitude doesn't really matter. In fact, the force of gravity at say the sort of nominal boundary of space, 100 kilometers, is almost exactly the same as it is on the surface of the Earth. So like if it's a few percent lower than the surface of the Earth. So in order to go up and stay up, the only thing that matters is how fast are you going horizontal to the Earth's surface. So you have that outward radial acceleration, or think of it like maybe like tetherball or something like that. It's really that outward acceleration is the thing that matters. And so when the rocket is going to orbit, the only reason it's going up is to get out of the thick part of the atmosphere. Because at high velocity, the atmosphere is thick as molasses. And so it goes up very briefly, but if you look at a long exposure of the rocket's trajectory, you'll see it goes up, but immediately curves over and starts going horizontal. And so at the point at which the point at which the stages separate, those two stages,
booster separation confirmed.
The primary boost stage, which is the most expensive part of the rocket, the point at which that staging occurs can be as high as Mach 10. But it's going away from the launch site at 10 times the speed of sound. So in order to get back to the launch site, you would have to have enough fuel and oxygen to reverse out that velocity and boost back all the way to the launch site. And you just don't have, the physics of it don't really allow you to have that much. It's not about saving money on fuel or anything, it's just physically impossible. Because another sort of thing about if you're in space is that there's nothing to react against. So, like whereas an aircraft can circle very easily because it's reacting against air, in vacuum there's nothing to react against. So the only way to go back the other direction is to apply just as much energy as it took you to go. If you want to go backwards, you have to apply just as much energy as it took you to go forwards. In fact, well, twice as much, really, because you've got to zero it out, and then you've got to...
So you've got to land elsewhere.
Yeah, so bottom line is this thing is zinging out to sea at 10 times faster than a bullet.
It may well be over the ocean, because the ocean covers most of the...
Oh, it's actually, at the point of separation, it's not that far away. It's maybe 100 kilometers away from the launch site, but it is going like hell in the opposite, away from the launch site. So the only way to really land it is to have it continue on that arc, that ballistic arc, and then land far out to sea on a ship that's pre-positioned to a particular latitude and longitude, very, very precise, to within about a meter. And then the rocket will then go from vacuum through rarefied air at hypersonic velocity. So when it's in vacuum, it has to, obviously you can't use aerosurfaces, you have to use nitrogen jets to control the attitude and position.
You see the first stage is already being a turnaround, and you can see the nitrogen from our attitude control system helping guide it back.
And stage separation has been confirmed. And you can see the first stage there flipping back. Use the nitrogen thrusters.
And then as it starts to encounter the air, we use grid fins, because grid fins look like sort of like a waffle.
And as you guys have noticed, the grid fins have deployed on the side boosters as well as the center core. Those work to help guide the boosters back to a nice targeted soft landing.
They work quite well across a wide regime, from both very high velocity hypersonics through supersonic, transonic, and subsonic.
They're stowed at the base of the vehicle and made up of state-of-the-art carbon fiber and aluminum honeycomb.
Stage 1 transonic.
So it's hard to have aerosurfaces that work well across that entire regime. And then, so once the air forces become high,
The Cape getting closer and closer. What a cool view. The first stage is passing through the cloud layers right now.
it uses the 4 grid fins to sort of control its attitude.
To land itself.
Yeah, it's controlling it's controlling pitch, yaw, and roll with the grid fins. And then those grid fins will then position it to where it's fairly close to the ship, and then it will light, in this case, 3 of the 9 engines to arrest the velocity, and then drop to 1 engine for precision right before landing.
Right. So why is that important? Why has this moment been important for you?
Just a very tough engineering problem. In the last 12 months or so, I've come to the conclusion that it can be solved. And I think SpaceX is going to try to do it.
Falcon 9 is essentially standing on the shoulders of titans, as they like to say in literature. We've built upon a lot of those lessons, the things that NASA has learned. We've taken that, but used kind of a clean sheet of paper that says, how can you build a rocket knowing that we want to do things that have not been done before?
Well, so in order to reuse the boost stage, which is about 70% of the cost of the rockets.
For the first stage, it starts its engines back up. It flips itself around, and the whole first stage is re-entering the Earth's atmosphere and slowly making its way back down for a landing on a drone ship that is out in the Atlantic Ocean.
Landing legs have deployed. And Falcon 9 has landed.
So that,
What cost is that? How much is that?
well, I mean, it's sort of on the order of $30 to $35 million.
Right, so you want to save that.
Yeah, I mean, it's like, I tell my team, it's like, imagine there was a pallet of cash that was plummeting through the atmosphere, and it was going to burn up and smash into tiny pieces. Would you try to save it?
Right.
Probably yes.
Yes, okay.
Yeah, that sounds like a good idea.
Right, okay.
So yeah, so we want to get it back,
Right.
and that way we don't have to make another one.
Oh my God.
Side boosters landing legs have deployed. LZ1, LZ2, both side boosters have touchdown. Landing operators move on to 11.100 on recovery 1 and recovery 2.
Stage 2, AFTS has saved.